Hello everybody, and welcome to this lecture on computer architecture. Today I want to talk to you about the truth tables and what they do, what they help us to design the logic circuits that we're going to build and the computer we're going to build eventually. We take it very slowly, we build everything starting from very simple ideas, and let's go back then step by step. Let's go back by the important observations that we had. Remember that we started with the Huntington postulates. If you forgot what it is, just go back to the lecture on Huntington postulates, and those are the basis for how our computer works. The computer implements our Huntington postulates, and those were the four basic ones that we found here. Is that we had operations AND and OR, represented here by dots and plus signs, AND and OR. So we had four of those postulates actually. Four of those results, immediate results we got from the postulates is that A AND 1 equals A, whatever A is. A OR 0 equals A, whatever A is. A and not A equals 0, and A or not A equals 1 for every value of A. And we already know now that our entire logic is binary logic, so A can only take the values of 0 and 1. Then we derived some further, which I call here the important observations, namely that A and 0 is 0, A or 1 is always 1, independent of A and A equals A, and A or A equals A as well. Not A equals A. And these are the two I will not mention today, but on basis on this we can now actually start building more important gates, and for that we need the truth tables. So let me show you how that is done. I have here the idea. Let me put this on the side. So what we need to do, we have some kind of circuit. Let's say we have here our AND circuit, which we call, we can write like this. We have an output and we have two inputs, let's call them A and B. So the function how this gate works can also be for other gates. What we have to do, we have to describe what the output is for all combinations of the two inputs A and B. So let's do this for our standard fundamental gate, which is the AND gate, which is this one. We can actually derive this on basis of these basic observations. Namely, let's see what we have to do. We say A, B, what combinations can we have? Well, A can be 0, B can be 0, A can be 0 and then B being 1, and A being 1, B being 0, and A 1 and B1. These are the four possibilities of the input, because any one value A or B can only take on the value 0 or 1. So we have two possibilities for either, and then 2 times 2 for A and B is 2 times 2 is 4 possibilities, 4 combinations possible. And I write them in this order so that when I read this and I ascribe here the least significant digit and here the most significant digit or bit, let me write like this. So now it reads here like it already reads like a number. I like the way this is done like this, so that here this reads as 0 times 1 plus 0 times 2, 1 times 1 plus 0 times 2, 0 times 1 plus 1 times 2, 1 times 1 plus 1 times 2. This is our binary number system, if you remember one of our earlier lectures. Now, so this reads then as 0, 1, 2, 3. That is nice. I have them ordered in this way. It's not necessary, but this is the way it's mostly done, and it's the way also how I like to do this. So now we have to give for all possible combinations, there are 4, we have to say what the output is. And then we write this, what is the function that we have here? We have here A and B. So this is what we call the AND gate. Well, what would be 0 and 0? Let's look here. 0 and whatever is 0. This is one of our basic observations we made. We actually proved them. Go back to the one of the previous lectures if you forgot how that worked. So also here 0 and 1, 0 and 1, well, 0 and A can be 1, then it's 0. 1 and 0, we can substitute for this one A, we can substitute this 1, and then here and 0, this is still 0. And now 1 and 1, so we have here 1 and 1, we can substitute in this rule that we found, we can substitute 1, and we found A and 1 equals A, so 1 and 1 equals 1. So now we have here a table where we have plotted, where we have written all the output values possible for all input combinations possible. And this is what we call a truth table. And this is the truth table for AND. And we can write this in a logic, in a graphic form. We can write it like this. Often it's also written, for instance, by other books or other works. They write this AND symbol. That is already, we're nearly programming. And then you have this one. It's mostly used by C programmers. Now we have, of course, we have other gates. So what other gate do we have? For instance, we have our OR gate. This is the other one. Let's also do this one, how that it works. The OR gate, this would be this one, A, B, and out. Let's also make this truth table, A, B, and then here on the output we have our OR gate, which is then A or B. And in the same way I would write 0, 0, 0, 1, 1, 0, 1, 1. These are all the 4 possibilities of writing the numbers, the inputs. These are the 4 possible input combinations. And I can find out what would be 0 or 0. Well, I can make use of this one, for instance. 0 or 0, I substitute in this one A equals 0. So A equals 0, 0 or 0 would be 0. And 0 or 1, we can substitute in this one that I have here. 0 or 1 equals 1. And in the same way, of course, I can exchange these two and then I get 1 or 0 equals 1. As you remember, the laws, Huntington postulates, you can exchange the two operands and the result at the output will be the same, always. So now you get here the last one, 1 or 1. What would it be? Well, I will substitute in this one, for instance, 1. So 1 or 1 equals 1. So this is then the truth table for the logic gate OR. Now, furthermore, you can write this thing also, this one can also be written as is more internationally way of writing it would be this symbol, but it doesn't matter so much. This is actually just a way of writing things. This would be the OR symbol for also from computer languages. The next gate we can do then is we can invert this gate, and the inversion would be writing a dot, a circle after this. So here or here, that would be here, that would be then become the NAND, or here that would become the NAND, which is called the not AND. And the not AND, so this would be NAND, or you can also write it like this, A and B and then not. That is of course then inverting the output. So the 0 becomes a 1, the 0 becomes a 1, the 0 becomes a 1, and this 1 becomes 0. So now we have the logic NAND gate. And we can do the same for the OR. That would be then writing here an inverter at the output and writing it like this. So this becomes the NOR gate. I can also write it here, NOR. So that would be A or B, but then not. And I can write this, the 0 is inverted into a 1, the 1 is inverted into a 0, the 1 is inverted into a 0, and the 1 is inverted into a 0. So now we already have 4 possible gates. We have the AND, we have the NAND, and we have the OR and the NOR. Later we will see that actually the NAND and the NOR are the favorite gates because they are simpler. The next one that I would like to do, let me put here a new page. If I can make here a new page. Okay. That would be a simple gate, which is just the inversion. and for that one we just have actually one operand, and we either write it like this, which would be the NOT gate, or I just write just a small circle, and that would mean negation. Anywhere in the circuit when you see this, you will have to imagine it's a negation, and that has just one input. So the truth table is just A, and then we would have not A. What would it be? Well, with one input you have only two possibilities. You have 0 and 1, and then the output is 1, 0. So that is another gate. Actually, I could put here A, and then I could put here B, and B is not doing anything. So now we have 5 gates. 5 gates. We have AND, NAND, OR, NOR, and we have NOT. So in this case, this is not A. We can also make one that is not B. So actually, how many gates can you make with 2 inputs? Well, I made here a summary. Let me show you this here. A summary of all possible gates, which I've put. Let me see, where am I? Here, put it here. It's a little bit written here on the side, but it's A. We have A and B as inputs, and we already have here our gate A and B, which had as the output 0, 0, 0, 1, as you know. So how many gates can you make? Actually, different gates. That would be actually 16, because I just write down here all possible output combinations. So I write for 0, 0, 0, that can be then 0. 0, 1 will be 0. 1, 0 will be 0. 1, 1 will be 0. So it will always be 0. That is a combination. It's possible. So it will always be 0 independent of A. I just call this just ground, or I call it more generally in mathematics, I would call it false, or call it simply 0. And then all possible combinations there are, because there are 4 bits here in the table. That means that you have 2 to the power 4 is actually 16 different gates are possible. Some of them are silly, I would call it. This is false, and is true, which is always 1. The gate is called true. You have here just copying A. The output is the copy of A. You have the output is copy of B. I don't call it a gate. I call it just a electric wire. And we have things like not A and not B. These are actually the standard simple unary gates, which we already described. But we also have the classics, the standard A and B. We have the standard A or B. We have the standard A nor B. And we have the standard A NAND B. So these are actually the classics. We call them more the fundamental gates. You have NOT. The NOT gate is unary. You have the AND gate. You have OR gate, NAND gate, NOR gate. And actually this one is also quite often used, is XOR, or actually called exclusive OR. So that is very similar to the OR gate, except, let's compare it here. You have A or B, which is this column here. I hope that you can follow where I am. A or B. So that is the output combination is 0, 1, 1, 1. 0 only when both A and B are 0, and it is 1 when both A and B are 1. And the exclusive OR, where do I have it? A exclusive OR B is 1 when either A or B are 1, but not both. So exclusive OR is different from normal OR by the last line in the truth table, that for an OR gate it is A1 or B1, and for the exclusive OR it is A1 or B1, but not both. That is the difference. So these are the basic gates in which we're now going to build our further our circuits. We're going to constantly make the circuits more complicated, and we will see how we get emergent properties, like we can do calculations, normal arithmetic calculations, and we can actually also start programming on basis of this. I want to finish here with this lecture that the names that we're giving here, that AND and OR and NAND and NOR, that is just a human interpretation, and that is not actually has anything to do with that it needs to be like this. For example, as I say here, an AND gate, this AND gate, where do I have it? A and B, for example, is named as such because if we assume a high voltage is true, written down as 1 here, and applied at both entrances, then and only then the output voltage is high too, meaning true or 1. So we could also use other logic. We could say that 0 is actually true, and then this would not be called an AND gate, but it would be another gate. I will let it to you to find out then which gate that would be. But that is what we call positive logic, that a 1 is actually true and a 0 is false, and then the output is true if both the inputs are true. And that is what we call positive logic, because then we associate 1 with true and 0 with false. So this sums up the lectures on truth tables. In general, truth tables, they summarize the output for any combination of the input bits that the gate has as inputs. Okay, I hope you enjoyed this lecture.